Hello students, now we are back to our organic chemistry series where we left off from last year. So last year we had arenes as the last organic chem topics. So if you try to recall, we did an introductory organic chem where you are being introduced to stereochemistry, like for example cis-trans isomerism and stereoisomerism such as enantiomerism. Okay, and then you learn about a little bit of nomenclature, and if you try to recall, I mentioned that you do not really need to memorize the nomenclature because you're going to encounter them again as we progress through the functional groups. Yep, then immediately after that you learn about alkanes. Okay, so for alkanes, if you try to recall, the only reaction which you have learned is, in addition to combustion, of course, the new mechanism which you have learned is free radical substitution. So for example, let's say we have propane here. Then if we subject propanes to chlorine under UV light condition, so potentially we can get either 1 chloropropane or we can get 2 chloropropane. Yep. So these are the two compounds which we can potentially get if we are looking at mono substitution. Of course, under UV condition, if it's uncontrolled, then you can get multiple substitution. Yeah. So these are the two compounds that are representative of what we call halogen derivatives. Yeah. So they are known as chloroalkanes. And these are very useful compounds which we didn't quite touch on last year. Okay, then after alkanes, you learn about alkenes. So in alkenes, you learn about a mechanism known as electrophilic addition. Okay, so if I'm going to give you an example to give you exclusively 2-chloropropane, what we can do is to add HCl gas and then to propene. Of course, it's not really exclusively 2-chloropropane. Maybe you get about, say, 80% or 90% of it. Yeah, and in a chapter under alkenes, you learn about stability of carbocation because you learn that in electrophilic addition, it goes through an intermediate known as a carbocation. Okay, so if you want a little bit of recall, so what happens in electrophilic addition is that for HCl, the bond is polarized. So H takes on a partial positive charge, Cl takes on a partial negative charge. So the pi bond will actually attack the H, and then the HCl bond will break hydrolytically. Okay, and then in the process, I'm generating a secondary carbocation. Yeah, so potentially I can generate primary carbocation. Okay, but this is less stable. Okay, so this primary carbocation less stable than secondary carbocations. So in terms of stability, because it's less stable, so it will be formed less favorably. Yeah. And you also realize that you can produce chloroalkane through electrophilic addition to alkenes. Okay, then shortly after alkenes, you learn about arenes. So in arenes, you learn the third mechanism in your H2 series for organic chem. You learn about electrophilic aromatic substitution. Yeah, so the reason why you don't want to go electrophilic addition is because as the reaction proceeds, it prefers to restore the aromaticity of the benzene ring or of the phenyl ring. So because of that, substitution is preferred as compared to addition. Yeah. So now we are moving on to the fourth topic, and you are also going to be introduced new mechanism. Yeah. So you have probably heard about them from your seniors. They are known as nucleophilic substitution. Yeah. So why is nucleophilic substitution important? Because we are able to transform the halogen derivative into many other possible functional group by simply replacing the Cl. Okay, so if you look at the CCl bond actually takes on a partial positive charge at the carbon bonded directly to the Cl, and then the Cl will take on a partial negative charge. So because of that, the carbon directly bonded to Cl, we say that it is susceptible to nucleophilic attack, meaning it will be attracted to nucleophiles. Okay, and that is essentially our main focus for this particular topic. Okay, so without further ado, we'll move on to this particular topic. If you look at the learning outcomes, there are quite a bit, but the focus is largely on the mechanism known as first-order nucleophilic substitution and second-order nucleophilic substitution. You can see the term being repeated a few times, and you are probably aware that these are the main focus, so we will talk about them slowly later on. Okay, yeah, so as an introduction, there are certain compounds in our daily life, for example, thyroxine, that is a halogen derivative. Okay, so in this case, it contains the iodo group. Yeah, but most other halogen derivatives are man-made. I think those of you who live long enough, or you have read before from your econs or GP, you probably heard about CFCs. Okay, chlorinated compounds tends to be carcinogenic, so if you're interested in it, you can read more about it outside the lecture. Yeah, but one thing I can share with you, a potential carcinogen is CH3I. This is known as iodomethane. The reason why this is a potential carcinogen is because the iodo group, in this case, it's a very good living group. And the Ci bond is very weak. So if a person accidentally breathed in some iodomethane into his body, right, then the nucleophilic sites in our body can potentially undergo nucleophilic substitution with iodomethane, and it will cause many of those nucleophilic sites to be methylated. And that is not something we wish to happen. Yeah, because when that happens, especially on DNA, right, then you're going to get into serious trouble, because it may lead into some form of mutation, and maybe your DNA cannot produce the necessary proteins which is needed for your survival. Okay, so if you read from, you can just try to Google iodomethane as compared to, say, chloromethane. Iodomethane is a much stronger carcinogen as compared to chloromethane. Okay, yep. So halogen derivative, basically the alkenes. One of the H is being replaced by the halogens, as you have seen from free radical substitution for alkenes. Okay, so just now, earlier on, I have already named you two of them. One chloropropane, so this is one propane, and then the other one is 2-chloropropane. Okay, those of you who are worried about nomenclature, you just need to know how to do basic naming. I think that is good enough. Okay, so we have bromoethane here, and then we have 1,1-dibromoethane, because the two bromo groups is substituted to the same carbon, and that carbon is designated number 1, and then you have 1, 2, and then 3-chloropentane. So if you try to label the carbon 1, 2, 3, 4, 5, regardless of whether you do it from left or right, the one in the middle is still carbon number 3. Okay, so Halogenoalkanes show constitutional isomerism. If you need a little bit of revision on this term, constitutional isomerism is what you have learned in secondary school, which is known as structural isomerism, and then as well as enantiomerism. Okay, so let's say for C4H9Br, you were told that there are 5 isomers. So if we move on to exercise 1.1, you are required to draw the 5 isomers of C4H9Br. Yeah, so the simplest way to determine all the potential isomers is to first draw a straight chain. Okay, so if we have 4 carbon, and then we'll draw a straight chain, 1, 2, 3, 4. Okay, so this is the longest possible chain, and then we'll try to branch it like this, and then from here we will then insert the BR at the appropriate position. Yeah, so maybe before I move into inserting the BR, one question you might have in mind is, how do you know that C4H9Br is saturated? Of course, the question or the statement sort of mentioned that it is an alkane. Yeah, but then how do we know that it is saturated if, let's say, in the future we are given some structural elucidation kind of questions? Okay, so we know that it is saturated. If you recall from last year, I did mention about something known as the degree of unsaturation, or otherwise known as the index of hydrogen deficiency. Okay, so if you recall, for 4 carbon, the maximum number of hydrogen it can take on will be 2n plus 2. Okay, so for a 4 carbon, the number of H, the max number of H, if it were an alkene, right, is actually equals to 2n plus 2. So 2n, 2 times 4, plus 2, which is equals to 10. Okay, in this case, it has only 9H, but it doesn't really matter here. Remember, earlier on, we mentioned that halogenoalkanes are alkanes with 1 or more H replaced by halogens. Yeah, so therefore, we can treat the Br as a H. So therefore, this formula can be sort of reduced to C4H10. Yeah, so in this case, when we try to calculate the degree of unsaturation of the above compound, it's actually 10 minus 10. Why is it minus 10 here? Because remember earlier on, I mentioned that the Br, you can treat it like a H when you calculate degree of unsaturation. So this is a 10. Okay, then what about the other number? So the other number is what we determine from the maximum number of H, as though it is an alkene, so it's 10. So 10 minus 10 divided by 2 is 0. Yeah, so we conclude that this compound is saturated. Okay, yeah. So with that, then we should be quite comfortable in drawing the rest of the constitutional isomers and enantiomers. Okay, so we will just continue from here. Okay, so from the above compound, the straight chain one, there are 2 potential positions where we can place our our Br. So we can place it at the first position. Okay, so we'll get this, and then we can place it at the second position, and we'll get this. You'll notice that when we place it at the second position, that second carbon is actually a chiral carbon. Okay, yeah, so because it's bonded to 4 different groups. Yeah, so if you're in doubt, please draw it out and take a look. Okay, then what about for the branch version? So for the branch version, again, we can potentially insert the Br here and the Br here. Okay, so if we insert the Br at the first carbon, so we are going to get this, and then the middle carbon, we are going to get this. Yeah, so the total number of isomers will be 1, okay, and then 2, but we need to count it 2 times because it exhibits enantiomerism, so therefore we need to consider the mirror image and itself as separate compounds. So 1, 2, 3, 4, and then 5. Okay, yep. So there are a total of 5 isomers. So we have successfully identified them. Okay, and then for part B, we need to give the IUPAC name of the 4 constitutional isomers. Okay, I don't think this is going to be extremely difficult, so let me just use a different ink. Okay, so in this case, as I said, you always start off your numbering from the smallest number of carbon. So this is carbon number 1, so we will call this 1 bromo butane. Okay, and then if this is 1 bromo butane, your second one will be called 2 bromo butane. Okay, yep. Then what about 4 and 5? So 4 and 5, again, we need to look at which carbon is being branched out. Okay, so the bromo group, it's being the functional group, you take on number 1. Okay, so 1, 2, 3, and then so the longest chain is is a propane. So the first position is a bromo group, so we'll call it 1 bromo. Okay, 1 bromo. And then the second position is a methyl group, so 2 methyl. Okay, and the parent is propane, so propane. Okay, so I hope you do recognize that naming, giving IUPAC name to organic compounds is quite systematic. At least the simple one, you should be able to guess it, or make a good educated guess if it comes out in exam, and you don't really need to memorize the list which appears somewhere in your introductory organic chemistry notes. Okay, then for number 5, what you're going to have is, again, we do the same thing, 1, 2, 3. Yep, so again, the parent is propane, so I'm going to write propane at the back. Okay, so instead of 1 bromo, now the bromo group is in the second position together with the methyl group, so it's called 2 bromo. Okay, 2 methyl propane. Okay, yeah, so I hope you do find the naming, I won't say intuitive, but it's not too difficult to come up with the names if you are more familiar with organic chem. Okay, so with this, we'll move on to the next portion on classifying them as primary, secondary, or tertiary. Yeah, so you might have seen from some online resources or even our own lecture notes that a primary center, right, can be denoted by 1 degree. Secondary can be denoted by 2 degree. Tertiary can be denoted by 3 degree. But please take note that you're not supposed, I repeat, you're not supposed to pronounce it as 1 degree, 2 degree, or 3 degree. It should be pronounced as primary, secondary, and tertiary respectively. Yeah, so I don't want to hear any one of you saying it's 1 degree, blah, blah, blah. Okay, so that will be incorrect. Yeah, how do we determine whether a center is a halogen derivative is primary, secondary, or tertiary? Yeah, so that is actually quite straightforward. There are 2 ways to look at it. The first way is simply look at the number of alkyl groups bonded to the said carbon. Okay, so I'm just going to do some highlighting for you. Okay, so this is the carbon that is directly bonded to the halogen, in this case, the iodine. Okay, then I'm going to highlight the alkyl group. So there's only 1 alkyl group, which is the one in baby blue. Yeah, so if there's only 1 alkyl group, we will designate this as primary. Okay, so same case go for the other one. So this carbon is the one where your chloro group is being bonded to. Okay, and then this carbon is where your bromo group is being bonded to, and then the alkyl group is just this whole chunk, and then this whole chunk. Okay, so all of these are primary. There is another perspective which you can take. As I often mention, all road leads to Rome. Especially for chemistry, many perspectives you can take. So another way to decide if it's primary is to look at the number of hydrogen, okay, the said carbon is bonded to. So in this case, for primary carbon, there will be 2 H's it's bonded to. Okay, so you can just count 2, 2. Yeah, and true enough, these H's are what we call primary H. Okay, primary H. Yeah, I mean, good to know the nomenclature. Okay, so then I think it's not too difficult to decide whether the center is secondary. Yeah, because in our case here, this is the carbon bonded to the halogen. This is the carbon bonded to the halogen. And then if you try to decide how many alkyl groups, in this case we have 2 alkyl groups. Yeah, and then in this case we have 2 alkyl groups, like this. Okay, so all these are designated as secondary. Okay, if you choose to look from the perspective of the H's, so there's 1 H here. Yeah, so again, secondary carbon will have 1 hydrogen, and secondary carbon will have 1 hydrogen. Okay, what about tertiary? Okay, what about tertiary? For tertiary, I think it's the same logic. First of all, you look at the carbon the halogen is bonded to. So bromo is bonded to this carbon, bromo is bonded to this carbon. Then you count the number of alkyl groups. So it's 1, 2, and 3. And then 1, 2, and 3. Yeah. So for tertiary halogenoalkanes, contains 3 alkyl groups. Secondary, 2 alkyl groups. Primary, 1 alkyl groups. So I hope that's straightforward. Okay, we'll move on to exercise 1.2, which reads, you are supposed to draw the structure formulae of the halogenoalkanes in the table and classify them as primary, secondary, or tertiary. Okay, so first, 3-chloropropene. Okay, so the structure is being drawn. If you are required to draw the skeletal, it will look like this, Okay, so off the top of my head, if you go by what I said earlier on, there's 1 alkyl group, so therefore we classify this as primary. Okay, you can either spell it out or you can just write the short form. Yeah, but maybe a little bit of examination technique. If you are being asked specifically in the question, classify as primary, secondary, or tertiary, you're supposed to spell it out. Yeah, but in the course of drafting an answer for a long question, right, you can actually write the short form, like 1 with a superscript 0. Okay, I better say 1 with a superscript 0 rather than call it 1 degree, because if not, then many of you will just call them as 1 degree, 2 degree, 3 degree. Okay, so the proper way to call them is primary, secondary, tertiary. Okay, so next we have chlorocyclopentane. So we have a pentane and then a chloro group. So again, if you just do a quick count, there are 2 alkyl groups bonded to the said carbon. So this will be secondary. And then 1 bromo, 1 methyl cyclohexane. So cyclohexane. Okay, the center we have 1 methyl group and 1 bromo. Yeah, so again, there are 3 alkyl groups bonded to the carbon directly bonded to the bromo. So this is classified as tertiary. Okay, so I hope you find this classification straightforward. Next, what about a halogen directly bonded to the phenyl ring or benzene ring? So in this case, we will classify them as like halogeno benzene, in this case chlorobenzene. And then if you're going to name this, then the halogen will take precedence. So in this case, 1 bromo, this is position 1, and then 3 methyl benzene. Yeah, so these are called halogenoarenes. Okay, then some of you might be asking, what about the chloro group directly bonded to sp2 hybridized carbon, which is part of an alkene? Yeah, so these are called chloroalkenes, or you can just call them halogenoalkenes. Okay, later on you might take note that halogenoarenes and halogenoalkenes, they share some similar characteristic when it comes to nucleophilic substitution. Yeah, but we'll go into that later. Okay, so next we're going to look at physical properties. So again, I hope you don't find this too boring, because throughout all the functional group, you will always encounter physical properties as part of as one section of the notes or subsections of the notes. Yeah, that's because we have to share with you on their states at room temperature, at least for the simpler halogenoalkenes and arenes. Yeah, and fundamentally, if you find studying the physical property a little bit challenging, you might want to go back and revise the topic on chemical bonding. Yeah, because chemical bonding forms the foundation of what you need to know for all the physical properties. So if you find that you are a little bit weak in trying to understand whether is it hydrogen bonding, or is it dispersion forces, or is it permanence dipole interaction, then you might want to review a little bit of chemical bonding before you study organic chemistry. Okay, yeah, so for halogenoalkanes, they are generally colorless. Okay, generally, so immiscible and usually denser than water. Yeah, and boiling point is higher because they form stronger dispersion forces, or you can say that they form stronger instantaneous dipole-induced dipole interaction than their corresponding alkanes. The reason why this is the case is because halogen has a much larger electron cloud as compared to hydrogen. Yeah, so this makes the electron cloud of halogenoalkanes more polarizable, and therefore it has a greater probability in forming stronger dispersion forces as compared to its alkane counterparts. Okay, yeah, then this last paragraph, this last statement, you might want to take note of it. For the same alkyl group, boiling point increase in the following order. It might not be very intuitive. Okay, as I said, it might not be very intuitive. Because in your mind, right, the C-Cl bond has a greater polarity difference as compared to a CBr, and in turn as compared to a Ci. Then why is it that the boiling point of iodoalkane is the highest? So in this case, permanent dipole interaction takes a back seat. Yeah, so induced dipole interaction or dispersion forces becomes the main intermolecular forces of attraction at play. So we will focus on how polarizable the electron cloud is, and the more polarizable, the greater the probability of forming stronger dispersion forces, and therefore the higher the boiling point. So we'll use this as the main idea to decide the order of the boiling point for the same alkyl groups. Okay, so we will have an exercise 1.3 to tackle this. Yeah, so for 1.3, boiling point of some organic compounds given. So you have propane, 1 chloro, 1 bromo, and 1 iodo propanes. You realize that propane has the lowest boiling points. I think it's understandable because BCD, all of them has halogens, and therefore much larger electron cloud as compared to propane. Yeah, so therefore if you're asked to explain why the boiling point of B is higher than that of A, then you can talk about the size of the electron clouds of 1 chloropropane is bigger than that of propane. Okay, so it has a larger and more polarizable electron clouds than propane. Yeah, so because it has a larger and more polarizable electron clouds than propane, it is able to have a greater probability of forming stronger dispersion forces. Yeah, and boiling involved overcoming these dispersion forces, so therefore 1 chloropropane has a higher boiling point as compared to propane. Okay, and then for part B, the boiling point increases in the order B, C, D. So again, I'm going to repeat the same thing. 1 iodopropane will have the largest electron cloud size. Okay, so okay, so this has the largest electron cloud size than the rest. So that implies that it has the most polarizable electron clouds than the rest. So therefore, the probability of forming stronger dispersion forces between propane molecule is higher. Yeah, so because boiling involves overcoming these stronger dispersion forces, so it has the highest boiling point as compared to the rest. All right, so I hope you are aware of the main ideas which you need to use when it comes to explaining the difference in boiling points. Okay, so I think here we also have a little summary for you. The main forces of attractions are dispersion forces, and some of you might learn it as instantaneous dipole-induced dipole interactions. Yeah, the permanent dipole interaction is not very significant, and this is evidenced by the boiling points. Okay, yeah, so we're going to move on to the next section. Okay, on the preparation of halogenoalkanes and halogenoarenes. Yeah, so in the introduction portion of this particular sets of notes, right, I did mention or give you a slight overview that you can produce halogenoalkanes from free radical substitution of alkanes. Okay, so I think I mentioned this. Okay, but this is not a good method because you will get a mixture of halogenated alkenes, and it's difficult to control where you want to substitute the hydrogens. Okay, you can also do it through electrophilic addition of alkenes, which I demonstrated to you. How you can get 2-chloropropane from propenes. Okay, so if you are not very sure what's going on, you may want to review your notes on alkenes. Okay, you can also produce halogenoalkanes from the nucleophilic substitution of alcohols, which will be covered in the next topic. Okay, and then for halogenoarenes, it can be obtained via the electrophilic substitution of arenes, which again we will cover in, we have covered in topic 12. If you need a little bit of recall, basically you have a benzene ring, and then let's say you want to get bromobenzene. Okay, you want to get bromobenzene. Do you remember what you need to add? Bromines, okay, with a halogen carrier, FeBr3, which serves as a Lewis acid, okay, and in this case, your bromo group will be added as an electrophile to the benzene ring, okay, and then your Lewis acid will be regenerated. We'll move on to exercise 2.1 now. Okay, so draw the structure of the organic compound in each of the following boxes. Okay, so we have 2 butene here. So 1, 2, 3, 4. So this is, or you can say but2-ene. Yep. So regardless of whether the H adds to the left or to the right carbon, we will still produce a secondary carbocation. Yeah. So therefore, the compound we are expecting will be like this. Okay. So we'll be getting 2-bromobutane. Okay. Then bromine in CCl4. So bromine in CCl4. So this is electrophilic addition. So this is also electrophilic addition. Okay. And then you notice that the 2 bromine atom is added between these 2 carbon. So that means that originally the 2 carbon which I highlighted in green has the original double bond. So I'm going to draw the compound out like this. Okay, like this. Yep. In order for you not to draw more than the necessary number of carbon, right? Please number your carbon. So if you number your carbon, you won't make mistake. Okay, so original CC double bond is between carbon 1 and 2. Yep, so this is fine. Okay, yeah. Then we have methylbenzene here, chlorine in iron 3 chloride, with iron 3 chloride as the Lewis acid catalyst. Okay, so you expect this to be electrophilic substitution. Okay, so methyl group, as what you have learned in arenes, it is an electron donating group. In fact, it is weakly electron donating. The effect, I think I mentioned before, is called hyperconjugation, but we won't go into details. Yeah, so it will activate the benzene ring towards electrophilic substitution, and if you check our data booklet, the chloroelectrophile will be substituted in the 2nd and 4th position, okay, relative to the methyl group. So you should be drawing this as well as 4th position with the chloro. Okay, so these are the 2 compounds which you should be drawing. Okay, yeah, so again, if you are a little bit lost here, then I think it's good to review alkenes and arenes before you go, before you dive into halogenoalkanes, because once you are deep into halogenoalkanes, you find that the earlier topics might snowball. So yeah, so if you understand the earlier topics, at least 80%, 85%, or try to recall some of the things in the earlier topics, then I think it will help you to understand what is going on from halogen derivative onwards. Okay, next we'll move on to section 3, which is probably one of the most important section in the topic on halogen derivatives. Okay, so basically here we are focusing on nucleophilic substitution, but we are also discussing a little bit about elimination, which is another kind of reaction which halogenoalkanes undergo. Yeah, so if I were to give a short summary, so let me use the same compound which I illustrated in the beginning of this chapter. So in this case, I'm talking about 1-chloropropane. Okay, so for 1-chloropropane, it looks like this. If it were to undergo nucleophilic substitution, so we have a nucleophile here, usually it is either negatively charged or it has a lone pairs of electrons which is easily donated to the electron deficient sites. So where is the electron deficient sites? I can represent it by a delta plus here and a delta minus. Yeah, so we will be calling this particular carbon the electron deficient carbon, or you can say that the carbon with the delta plus is electrophilic in nature, so therefore it is susceptible to nucleophilic attack. And once it undergoes nucleophilic substitution, you will end up with the nucleophile replacing the Cl, so plus Cl minus. In this case, I will be able to balance the equation. Yeah, but we are also aware that nucleophiles on its own, right, can also display the behavior of a base. So therefore, we can also say that nucleophile is also basic in nature. So basic in nature here means that it can also fulfill its role as a base. So in that case, potentially, this reaction can also result in what we call an elimination reaction, where the nucleophile abstract a H from the neighboring carbon. So in this case, the nucleophile can abstract the H from here. So this is known as a beta carbon. So the carbon directly bonded to the chlorine is known as the alpha carbon. Yeah, so in particular, this kind of elimination is known as beta elimination. Okay, because it always results in the abstraction of the beta hydrogens. Yeah, so eventually you will end up with an alkene as well as the nucleophile abstracting the H. So what we get here is the conjugate acid, and then of course plus Cl minus. Yeah, so in certain cases, it's kind of like mentioned that the net of this reaction, it's like expelling out HCl, inverted comma. So it's like similar to the expulsion of HCl. Yeah, so such reaction in the past is also known as dehalohydrogenation. Okay, so I repeat, such elimination, right, in the past is also known as dehalohydrogenation. Yeah, but this name is not so common used nowadays. Okay, yeah, but just take note that the focus for H2 curriculum is on nucleophilic substitution in terms of the mechanism. Yeah, so I think earlier on in our learning objectives over here, so maybe I can just go back to the learning objectives. In the learning objectives, I think we highlighted the importance of the students understanding the mechanism of nucleophilic substitution, particularly SN1 and SN2. Elimination is not being mentioned for the case of mechanism. Yeah, so let me repeat. For mechanism wise, elimination is not required. Okay, but of course, if you want to learn about it, you can always refer to online resources, or you can ask your H3 friend, because elimination is in the H3 curriculum. Okay, so the H3 students for chemistry, they need to know how to draw the elimination mechanism. Okay, but I think our focus for this particular chapter, at least at this point in time, is on nucleophilic substitution. Okay, so so without further ado, I just move on directly to the mechanism. But I think I've explained part of this to you already. So as I mentioned, the electron deficient carbon, otherwise known as the alpha carbon here, has a partial positive charge, which is susceptible to nucleophilic attack. So that's another way you can describe it. Nucleophile generally has a negative charge, and if it's neutral, then it will have a low-lying lone pairs to be able to donate to the electron deficient center. Yeah, and this particular generic representation Okay, I have sort of highlighted above, okay, in the summary. Okay, so for the general mechanism of nucleophilic substitution, by and large, for the past 100 over years, you learn two types, or scientists uncovered two types. Okay, SN1, they are famously known as SN1 or SN2, so SN1 or SN2. SN1 stands for first order nucleophilic substitution. SN2 stands for second order nucleophilic substitution. Okay, certain textbook or online resources, they will call SN1 unimolecular nucleophilic substitution, for SN2 bimolecular nucleophilic substitution. So it doesn't matter how you describe it, as long as you and I are on the same page. Okay, then the generic mechanism for SN2 is being shown here. Okay, so maybe let me just showcase to you what are the important points you need to take note of. So first of all, for SN2 reaction, it occurs in one step. Okay, so simply just one step. Okay, and the rate determining step, okay, involved the nucleophile as well as the substrate. So in this case, I just represent the substrate. Okay, I'll just write it out: CH3 CH2Br. Okay, and in terms of kinetics, first order with respect to the nucleophile, first order with respect to the substrate. At this point in time, if you forget about your kinetics, I think it is good to review it a little bit, because it is of utmost importance for you to know how to work out the mechanism based on the kinetics data. Okay, this is in addition to drawing the mechanism using curly arrows. Okay, in case you forget, these are known as curly arrows, okay, which you need to be able to draw them out when you are asked to illustrate the mechanism, or maybe draw the mechanism. Yeah, so it's important for you to know how to make use of the curly arrows. Okay, yeah, so what is the characteristic of second order nucleophilic substitution? Okay, so first of all, the nucleophile approaches from the rear of the CBr bond. Okay, so you can see that the nucleophile actually approaches from behind. Okay, so behind is over here. So it approaches from the rear. So nucleophile approaches, maybe I can just write it out here. So the nucleophile approaches from the rear of the CBr bond. Okay, so so that means that one of the key points to consider for second order nucleophilic substitution is that the rear of the CBr bond must be relatively unhindered. Okay, so that means that ideally the rear this is ideal, okay, should be relatively unhindered. Yeah, so if the rear contains bulky groups, then that makes second order nucleophilic substitution difficult. So that makes the approach by the nucleophile towards the rear difficult, because it will undergo unnecessary steric repulsion with the large groups. Okay, so that is one criteria you need to consider. I do believe that as you scroll through your lecture notes, it's mentioned over there. Okay, and what are the key things, key points you need to consider when you draw the mechanism for second order nucleophilic substitution or bimolecular nucleophilic substitution? So in the beginning, right, it will be good for you to position your CBr bond horizontally like this. Okay, then after that, for the rest of the groups, you'll be projecting to the left, something like this. So if you look at it from one angle, right, it seems to be a cone being turned 90 degrees. Okay, so for example, I have a cone like this, so it's like being turned 90 degrees. Okay, so I mean, if that's a good description for you, you can take it as it is. So therefore, the nucleophile, right, actually approach towards the middle of the cone. Yeah, so this is like the cone over here. Okay, yeah. Then, so what happens after that? After that, right, it is important for you to realize that for the purpose of drawing second order nucleophilic substitution, it is important for you to draw the transition states out. And transition state involve partial bond breaking and partial bond forming. This is represented by the dotted line. So these are the dotted line. So dotted line. So dotted line represents partial bond breaking and partial bond forming. Okay, and the total charge of the transition state needs to be written. Yeah, so if you don't write the total charge, then you will not, you probably will be penalized, because the conservation of charge is important for any kind of reaction. Okay, and at the end of the reaction, you realize that if you use the same cone analogy which I mentioned earlier on, right, you realize that the cone is now like this. So the cone is like being turned inside out. What is the meaning of being turned inside out? So you imagine that this is like a paper cone, right? So I use my hands to push it in, and then I use another hand here to take out from the other side and pull it out. So this is like turning the cone inside out from the tip of the cone. Okay, so this is a characteristic of second order nucleophilic substitution. Later on, you will learn the term known as inversion of stereochemistry, or stereochemical inversion. Okay, so I can write this out here: stereochemical inversion. Yeah, so this is a very important characteristic of second order nucleophilic substitution. So the inversion of stereochemistry. Yep, and then of course the leaving group. Normally we will call the BR the leaving group, because it is the group that leaves the substrate at the end of the reaction. Yeah, so you have to remember to write it in. Yeah, so sometimes in exams the students will forget to write it in. Yeah, and then for those of you taking H3, you will notice from your H3 notes that for transition state, we tend not to write the word transition state below. Yeah, so we tend to use this particular symbol to represent transition state. It's what we call a double dagger. Okay, so if you go to the internet and search, this particular symbol is known as a double dagger. So a double dagger represents transition states. Yeah, so it is perfectly fine if you write the double dagger, but you don't write the word transition states. But for those of you taking H2, if you don't wish to use the double dagger, you can simply just write the term transition state below the square brackets. Yeah, so remember that transition state is not the same as intermediates. Okay, so this is not okay, intermediates. Yeah, so in the energy profile diagram, transition state occurs at what we call the local maximum. Intermediates occurs at what we call the local minimum. Yeah, so if you want a rough time frame, transition state exists in about 10 to the power minus 15 seconds. So in that case, it makes it makes locating and isolating transition state near impossible. Yep. So it's until I think in the late 80s to the early 90s, this particular chemist who won the Nobel Prize, known as Professor Ahmad Zewail, unfortunately he has passed away. He developed this area of chemistry known as femtochemistry, which allows chemists to study transition states. But again, studying it does not mean that the transition state can be isolated. Yeah, then in case you are curious for intermediate, how long does it last? So intermediate can exist for about 10 to the power minus 4 to about 10 to the power minus 6 seconds. So it's pretty long. I mean, it's very short in your eyes, but it's actually pretty long in the molecular system. So it's enough for you to abstract it out briefly and study it. Okay, so if you heard me, I'm going to just go through the written part of the notes so that you are not overwhelmed. So okay, CBr bond is polar, so it makes the carbon center electron deficient. The carbon center is also known as the alpha carbon. Okay, and then the formation of the the formation of the bond between the nucleophile and carbon happen at the same time as the breaking of the CBr bond. Okay, so this is important. At the same time, CBr bond is simultaneously weakened, and then the CBr bond is where is it? Okay, it's not written here, but the nucleophile and the carbon bond is simultaneously formed. Okay, maybe it's written at the back. Yep. And then you get a unstable activated complex known as a transition state. Yeah. So for the purpose of H2, if I did not emphasize earlier on, the drawing of the transition state is absolutely necessary when you are illustrating mechanism. Okay, especially if the question is kind of obvious that they are asking for bimolecular nucleophilic substitution. Okay, then so it's a one-step mechanism, I think I mentioned. First order with respect to the nucleophile, first order with respect to the substrates. Yeah, the RBR is also known as a substrate. If you heard me keep using the word substrate, yeah, that's what it means. Yeah. So the mechanism is known as second order nucleophilic substitution or bimolecular nucleophilic substitution. Energy profile is shown here. So this is the energy profile diagram. We are sketching energy against the progress of reaction, or I think in the more advanced version of some textbook, or even in H3, we call this the reaction coordinates. Okay, if you are interested to know why is it called reaction coordinates, you can read more about it. Yeah, but the proper term is reaction coordinates. So the activation barrier is between the total energy of the substrate and the nucleophile, and I mean the difference between the total energy of the transition state and the substrate and the nucleophile. So this is known as the activation barrier, which is shown clearly in the diagram or in your energy profile diagram. And then the delta H must also be shown, and it's exothermic. So that means that over here we made an assumption that the bond between the nucleophile and carbon is stronger than that between the carbon and the bromine. Okay, then of course you need to sketch the transition state. This is what we call the maximum point, or if there are more than one transition state or more than one intermediates, we will call this the local maximum. Okay, so that's how we should be drawing nucleophilic substitution. Okay, then I think over here the important thing is about the inversion of stereochemistry. Okay, so we have a reactant here. Okay, so you notice that if I'm going to draw a cone, it will look like this. So this is like the cone. Okay, and then after the reaction with OH minus, you notice that the cone actually turns inside out. So again, what is the meaning of turning inside out? So I put my hand here and then I pull out from inside, and then when I pull it out, this is how it looks like. Okay, so this is known as the inversion of stereochemistry. Okay, so that also means that the chirality of the carbon is preserved. Okay, maybe preserve is not the perfect word because why is preserve not the perfect word? So for example, let's say my reactant, right? Maybe it rotates plane polarized light, say clockwise. Okay, I mean I just give a random value, clockwise by 15 degrees. Okay, so for the product, right, what you are going to get it will be the pure version. So that means that there will not be a mixture of this particular enantiomer and its mirror image. You are only getting one particular enantiomer out. Yeah, so when you are getting one particular enantiomer out, probably it will rotate anti-clockwise, plane polarized, let's say by 20 degrees. Yeah, so you will not get a mix, because if you get a mix, right, then the plane polarized light will not be rotated, so it won't have no effects on plane polarized lights. Yeah, so this is a very important outcome you need to recognize. So when we say that the stereochemistry it's kind of preserved, it doesn't mean that the rotation stays the same. It just means that I will be able to get a stereochemically free, or rather stereochemically pure product at the end of SN2. Okay, so that is the meaning of stereochemical inversion. You might want to also recognize that SN2, I mean, for a particular substrate, it might occur via more than one pathway. So it's not a pure SN2 in most cases. It could be a mixed. Yeah, but sometimes for the purpose of H2 assessment, we tend to just narrow down the scenario into either 100% SN2 or 100% SN1, so that it's easier, at least at this stage, it's easier for the students to work out the mechanism. Okay, so if you move on to a slightly more advanced level, or in fact even for H3, there will be scenario where you might want to look at some data, and then from the data you might recognize that actually both SN2 and SN1 occur maybe at the same time, or maybe there's about slightly greater percentage of SN2 as compared to SN1, or vice versa. Yeah, so these are the things which you can obtain from the data if given to you. Okay, then next we're going to move on to SN1, or otherwise known as unimolecular nucleophilic substitution. In terms of drawing of the mechanism, it's a little bit more tedious as compared to SN2, but at the same time it also seems to be a bit easier. Yeah, why is that the case? Because there isn't a need for you to draw the transition state for H2, so maybe I should emphasize it. So for SN1, no need to draw transition states. Okay, this is largely for the purpose of H2 assessment, for the purpose of H2 assessments. Okay, however, I think this is something important which I need to share with you guys. There will be instances such as the MCQ question for Cambridge exam, right, that the students need to recognize the transition state for SN1. Okay, so there's a difference, to draw and to recognize. I think recognizing is easier because it's just a pictorial recognition. Yeah, so over here, I think I will also move on to showcase to you how to draw the transition state for SN1. Yeah, but that doesn't mean that you should be drawing it for your assessment. Okay, so let me showcase what you need to take note of, but maybe before that, the rate equation. So SN1, so first order with respect to the substrates. Okay, so in this case, it will be just RBR. Okay, first order. Yeah. Maybe I want to shift back a little bit. I want all of you to take note of one very important thing. Regardless of whether is it SN1 or SN2, right? The rate determining step involve both SN1 and SN2. For the rate determining step, both of them involve the substrates. That means that both of them involve the breaking of the C-halogen bond, and that also means that the strength of the C-halogen bond is of utmost importance in determining the rates of the reaction. Yeah, that is something you need to recognize. The difference between SN1 and SN2 is that for SN1, the slow step or the rate determining step does not involve the nucleophile. Yeah, so the nucleophile is only involved in the fast step. So if you recall from kinetics, that means that the change in the concentration of the nucleophile has no bearing in the overall rates of the reaction. Okay, so over here, in the slow step, involve the CBr bond breaking. So make sure you remember to draw the curly arrows. Okay, and then ensure that your intermediates is a carbocation over here. Okay, and then you redraw your carbocation, and then the next step, remember that your nucleophile donates the lone pair of electrons to the carbon center. The carbon center over here is electron deficient, and it bears a full positive charge. So this is not a partial charge, it's a full positive charge. Yeah, because after the CBr bond undergoes hydrolytic cleavage, the minus charge goes to bromine and the positive charge goes to the carbon. So the carbon is what we call a carbocation. You can call the center over here a carbocationic center if you wish to. If you do a quick counts there are 6 electrons around the carbon center. So when the nucleophile donates the 2 electrons, now the product has the carbon taking on an octet's configuration. Okay, and of course the nucleophile attack in the fast step. Yeah, so these are some of the details which you probably need to consider. And in most cases, we tend to draw the slow step as an equilibrium arrow. The reason is the CBr bond basically is vibrating about the center. Yeah, so there will be a point in time when the distance between the C and Br is too far apart, so that's considered almost the whole bond is being broken. And then there will also be a point in time when the CBr distance is quite near, so that means that there's a bond existing between C and Br. Yeah, so do note that the CBr bond do not just break as and when it likes lah. Yeah, so in reality, all bonds vibrate. So they do not just stay static. Yeah, so at certain point in time, they are a bit far away from each other. Certain point in time, they are nearer to each other. Okay, so that also means that if I were to ask you to draw the transition state out, okay, so the transition states, it's probably not going to be too difficult. So I will just call this TS1. So TS1 means the transition state between the starting material and the carbocationic intermediates. So that's TS1. Okay, so if I'm going to ask you to draw it out, I think you can easily tell me that everything else stays the same. Okay, CH2, CH2, CH3, and then CH2, CH3. Okay, so this is partial bond breaking between C and Br. Okay, and remember, transition state you represent with a double dagger. Okay, so if you don't wish to represent with a double dagger, you can simply just spell it out and just call it TS1, transition state 1. Okay, and also it will be good if you can just put delta plus over here and delta minus here. Yeah, this is more for the H3 student, and we say that as the bond breaks, the carbon develops a positive charge. Okay, and the same goes for the bromine. The bromine develops a negative charge. Okay, then next I'm going to move on to the transition state for step 2. So that means that when the nucleophile attack the carbocationic center, how does the transition state looks like? Okay, so the transition state, you can envision that it looks like this: CH2, CH3. Okay, and then the carbon is here, the CH3 is here. Okay, and then the CH2, CH3, and then a partial bond is formed between the carbon and the nucleophile. Okay, so we'll represent it with a double dagger as well. Okay, so that will be the transition state between this and the product. Yeah, so let me emphasize, the drawing of transition states for SM1 is not a requirement for H2. So for those of you who are listening up to this point in time, you don't need to worry about it for H2, but you probably need to recognize it if an MCQ question gives you some options. Yeah, so for those of you taking H3, it will be good for you to know how to draw the transition states. Yeah, because it will be covered in your curriculum. Okay, yeah, then yeah, moving on to some of the points which I mentioned. I think most of it I've mentioned already, so I'll just skip. But most importantly, you need to recognize that for SM1 is a two-step mechanism, and the rate law involved only the substrates. Okay, there is always a confusion between SM1 and SM2 because somehow the students think that 1 and 2 represent the number of steps. Okay, this is totally nonsensical. Okay, so the 1 and 2 represent the overall order of the reaction. Yeah, so please do not have this idea in your mind. Okay, so we have the energy profile diagrams over here. So again, as I mentioned earlier on, the intermediate is what we call the local minimum. And then over here is the first transition state, so TS1. So TS1 basically involves partial bond breaking between the carbon and bromine. And then we have TS2 here. So TS2 represent the partial bond formation between the carbon and the nucleophile. Okay, the carbon as in the carbon in the carbocationic intermediates. Okay, and I have illustrated it over here very clearly. So if you wish to, you may draw them out. Okay, then I will move on to the stereochemistry, because it is the stereochemistry of SN1 which probably requires a little bit of discussion over here. Yeah, so maybe I'll just move back here. If you notice that SN1 involve an intermediate which is a carbocation, and this carbocation intermediate, right, it has 3 different groups. Okay, so I will highlight in yellow. So it has a propyl group, okay, it has a ethyl group, and it has a methyl group. Okay, so there's a little typo here, you may wish to correct it. This is CH2. Okay, yeah, so you have an ethyl group over here. So that means that when the nucleophile attacks the carbon center over here, it will be able to generate a chiral center. Yeah, but because the carbocation is flat, meaning it is trigonal planar in geometry. So maybe I can draw this over here. So my carbocation, in terms of geometry, right, is let's say I draw a group projecting away. This is a methyl group, and then I draw a ethyl group projecting towards me, and then in the same plane is a propyl group like this. So this carbocationic center is trigonal planar in geometry. So that means that when the nucleophile approaches it, right, if it approaches it from the top plane or the top face, so this is known as the top and bottom. Okay, if it approaches it from the top face, what you're going to end up with will be something like this. You have a nucleophile above, okay, and then I'm going to draw a bond down because it forms a bond with the carbon. Okay, and then you will notice that this whole portion, right, I'm going to flatten it downwards. Okay, sorry, not flatten it, but I'm going to push it downwards. Okay, so you end up something like this. So I will push this downwards. You need to maintain the tetrahedral geometry. Okay, like push it downwards, and then you project it downwards, and then the propyl group like this. Okay, my apologies for the messiness, but yeah, you get what I mean. Okay, so maybe I'll just erase some of this part so that you can see. Yep, and then when the nucleophile approaches from the bottom plane or the bottom face, yeah, this is what you will get. Okay, so again, because it approaches from the bottom face, right, the nucleophile will form a bond with the carbon. Okay, and all this group will be pushed up. Okay, so I'm projecting away and then projecting towards me, and then this group is the same. Okay, if you look carefully, right, this particular structure and this particular structure, right, they are what we call an enantiomeric pair. So I zoom out a little bit so that you can see. Okay, are you able to see that they are an enantiomeric pair? So if I draw a mirror plane here, you can see that they are direct mirror image, because this is here, this is here, this is here, and then this is here. Okay, so I hope you can see that. Yeah, so because of that, right, in the course of an SN1 reaction, we say that at the end of the day, we will get a racemate mixture. Okay, so that means that unlike SN2 where I will get a pure enantiomer, for SN1, I'm just going to end up with a pair of enantiomers which probably occur about 50% each, and they have no effect on plane polarized lights. And the reason why that is the case is because you notice that my carbocation is trigonal planar in geometry. So that means that when my nucleophile approach from the top and bottom plane, it will be able to approach in what we call in terms of probability, near equal probability of approaching from the top and bottom plane. Okay, and you will also notice that at the end of the day, right, when the nucleophile approach from the top and bottom plane, the transition state is an enantiomer. Okay, so enantiomeric transition state have the same electronic energy. Yeah, that is a little bit out of the curriculum, but you might want to recognize it. So I repeat, enantiomeric transition states have the same electronic energy, and that is why at the end of the day, if the transition state has the same electronic energy, you cannot differentiate between the two in terms of activation energy. So that, because same electronic energy means that the activation barrier leading to the attack by the nucleophile from the top plane is the same as the activation barrier leading to the attack of the nucleophile by the bottom plane, from the bottom plane. So that means that you can't differentiate between the two. Yeah, you can only differentiate when the transition state energy are slightly different. So that is why chemist is able to do what we call as stereochemical reactions. Yeah, so that's not so straightforward. We'll discuss more of that in H3 if you are taking it. If not, I think you can just keep it as it is for H2. Okay, so I think I've mentioned what I need to mention over here. So maybe I can emphasize some of the important points again. So we have trigonal planar geometry about the electron deficient carbon's importance. Yeah, so remember that this whole intermediate is not trigonal planar. Why? Because these are all tetrahedral in geometry. Okay, so you need to be a little bit more specific when you are talking about the geometry. So it's trigonal planar with respect to the electron deficient carbon. So the nucleophile is able to approach from the top and bottom plane with near equal probability. Equal probability only when your substituent group is not or does not contain a chiral center. Yeah, but just for you to take note of. So therefore I'm going to end up with 50% of this and 50% of this, and this is a racemate mixture or racemates. Okay, so I will stop here as it is. I won't go into details. Probably for H3 then we can discuss more. Okay, so we have exercise 3.1 over here. So it reads, possible reaction hydrolysis of 2-chloro-2-methyl-propane is shown. So we have a slow step, generates a carbocation, and then a fast step produce the tertiary alcohol. So this is obviously SN1 because it occurs via 2 steps. So these are it's a 2-step mechanism. Yeah, so energy profile diagram definitely cannot be A and cannot be B. Okay, so it's either C or D because C or D both 2 steps. And which diagram best represent the energy profile diagram? So the difference is that for C, right, the product has a higher energy as compared to the reactants, and then for D, the reactant has a lower energy as compared to the product has a lower energy as compared to the reactants. Yeah, so that means that we need to see if the CCl bond is stronger or the CO bond is stronger. So if you flip over the data booklet, or even without flipping, you should be able to tell me that CO bond is definitely stronger than CCl bond. Yeah, number one is because carbon and oxygen are in the same periods. So same period, their orbitals have similar sizes. So there's orbital matching. CCl tends to have a little bit of orbital mismatched. And in addition, CO is a more polar bond as compared to CCl. So you expect the bond strength to be enhanced by electrostatic attractions. Okay, so therefore my answer will be donkey, D. Okay, so I hope you will pick D as the option. Then moving on, we have exercise 3.2. Okay, so halogenoalkanes reacts with aqueous alkaline. So one mechanism is shown here. So one-step reaction. So definitely as we are looking at SN2. Yep. If you are still unclear about the term SN1 and SN2, I suggest you stop the video now and then you just move back to the section when I was discussing SN2 and SN1. So that will give you a clearer picture and clearer view about what's happening. Okay, then question asks you which statements are correct. So the reaction is an example of nucleophilic substitution. I cannot deny this because once I read SN2, then definitely we're talking about nucleophilic substitution. And of course, you see that a halogen is being replaced by an OH. Yeah, so statement 1 is correct. Statement 2, between X and Z, the C halogen bond will be lengthening. So we need to be a bit careful here. X and Z, so C halogen bond will be lengthening. Yes, if you remember the transition states. Okay, so the transition state involve the partial bond breaking of the C halogen bond and the partial bond formation of the CO bond. So indeed, the C halogen bond will be lengthening. Okay, so this is correct. Then 3, energy difference between X and Y represent the activation energy. Of course, this is nonsense. The activation energy is between X and Z. Okay, so this is the activation barrier. Okay, so because 3 is wrong, I will only be choosing options 1 and 2. Yep, and then the next sections we have the effects of substructure of the halogenoalkanes on the relative rates of SN1 and SN2. Okay, so over here, for SN1, we need to explain in terms of the stability of the carbocationic intermediates. Okay, so over here, right, we get a relatively challenging looking or complicated energy profile diagram, but maybe I will just highlight in different colors so that it's easier for discussion. Okay, so for the tertiary one, I will just represent it like this. Okay, and then for the primary one, maybe like this. Okay, so here in case you are wondering, right, we are making an assumption here. So the assumption we are making is that for a primary and tertiary bromoalkane, right, we are assuming that they have relatively similar energy at the start, and of course for the alcohols, we have relatively similar energy as well. Yeah, so here what are we discussing is that number one, we need to be aware that the tertiary carbocation in terms of energy is more stable. In this case, is lower than that of a primary carbocation. Yeah, because from what we learned in alkenes, the part on carbocation under alkenes, a tertiary carbocation has 3 electron donating groups, okay, which are alkyl, as compared to a primary carbocation with only 1 electron donating alkyl groups. Yeah, so in that case, the carbocationic center for a tertiary carbocation will be more stabilized. Yeah, and because it is more stabilized, right, that means that the transition states leading to the carbocation should be more stabilized as well. Okay, so what do we mean? So I think the best way to explain this is to illustrate with an example. So let us talk about an isomer. Okay, I think it's easier. So we have say a primary bromobutane. So this is primary RBr. Okay, and then I will draw the tertiary counterparts. Okay, so this is a tertiary RBr. Yeah, so these two are isomers. So if you are able to draw the rest out, you can, but I'm only interested in these two. Why is it that I'm only interested in these two? Because number one, we need to make an assumption that the initial energy of these two are similar, and then of course the alcohols are also similar in terms of energy. Okay, but in the transition state leading to a tertiary carbocation, the energy is very different. Okay, so if you recall, okay, I just need to recall a little bit. Earlier on, I have shown you how to draw the transition states from the substrates. This is a substrate to the, or rather the transition state between the substrate and the carbocation, which is represented by this. Okay, so it involved the lengthening of the CBr bond. And as if you remember earlier on, I mentioned that the lengthening of the CBr bond also represents that the carbon develops a positive charge. Yeah, so in this case, the carbon will be a developing tertiary carbocation. Okay, so bear this in mind before we go into this. Okay, so that means that for this particular transition state, which I'm going to write in blue, right? So I just call this TS1. Okay, so for TS1, it will look like this. Like this, like this, like this, dot, 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 BR. Okay, this is a transition state. And you'll notice that this transition state has a developing positive charge at the tertiary carbon. So I'll just write developing positive charge at the tertiary carbon. Okay, then I'm going to do the same thing to the primary substrates. Okay, so maybe I should erase this. I will write it in another colored ink so that you are not so confused. Okay, so this is primary RBR. Okay, then I'm just going to call this TS1 as well. Okay, so for the primary TS1, right, it looks like this. Dot, 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 BR. Okay, transition state delta plus delta minus. So you realize that for the case of the one I've drawn in orange, right? Okay, so there is a developing positive charge, okay, at the primary carbon. Okay, and if I were to ask you to compare the stability between this TS and this TS, obviously you should be able to tell me that the one with a developing positive charge at the tertiary carbon is more stable as compared to that with a developing positive charge at the primary carbon. Okay, and consequentially, you know that the tertiary carbocation is more stable than the primary carbocation. Yeah, so that explains the relative difference in the heights. Okay, and of course, when you compare that, then if you just limit the amount of energy which you introduce to the system, meaning you don't input too much energy, then you will be able to recognize that I will only be able to form the tertiary substrates. So therefore, the formation of the tertiary alcohols, in this case, the tertiary alcohol via the SN1 pathway will be a lot faster as compared to the formation of the primary alcohol from the SN1 pathway. Yeah, so that is what this energy profile diagram is trying to hint to you. So you have a conclusion here. The rate of SN1 increase in the order of primary, secondary, tertiary. Okay, then as I highlighted earlier on, SN2, I think at the very beginning I mentioned that because SN2 involved the nucleophile approaching the substrate from the rear of the C halogen bond, so if the rear is directly hindered, like for example in the case of a tertiary halogenoalkanes with 3 alkyl groups, then your nucleophile will experience electronic repulsion with the alkyl groups. So once it experiences electronic repulsion, then it makes it difficult for the nucleophile to approach the rear. Yeah, so because of this, SN2 pathway for tertiary substrate will largely be shut off because it's likely to involve a very high activation barrier. Okay, so the rate of SN2 will increase in the following order. So primary substrate will react fastest via SN2, tertiary substrate the slowest. And then for SN1, tertiary will be the fastest, primary will be the slowest. Okay, so in short, we will largely expect primary halogenoalkanes to react via SN2 predominantly. Okay, tertiary to react via SN1 predominantly. Secondary will be either, but in reality it's actually both. Yeah, but for the purpose of simplicity, in the case of most H2 assessment, we will usually ask you to examine the kinetics data, and then from the kinetics data or other kind of data, you'll be able to tell whether is it SN1, SN2. So you don't really need to memorize whether is it SN1 or SN2, but I think in a very generic way, you probably want to know that primary substrate prefers SN2, tertiary prefers SN1. I think that is good enough. Secondary usually prefers both. So it's not exactly either, but it could, I mean, each of them will occur in a certain percentage. Okay, there are definitely exceptions to the mechanisms preferred by primary, secondary, and tertiary substrates. Yeah, so for example, this particular primary halogenoalkanes, known as 1-chloro-2,2-dimethylpropene. So if I'm going to sketch out the skeletal structure, it will look something like this. So it has a quaternary center here with a Cl. Yeah, so despite being a primary halogenoalkanes, right, you'll notice that it has a very huge bulky groups over here. Yeah, so although there are two H's here, so I'm going to draw them up. So although there are two H's here and it's considered primary, the shear steric hindrance, okay, provided by this large group, right, will deter the nucleophile from approaching from the rear. So it's difficult for SN2 to occur. I mean, it's not impossible, but it's just it's going to require a very high activation barrier. Yeah, and then for primary halogenoalkanes, there are also some which can occur via SN1. So for example, let's say we have this particular alkane, chloralkane with Cl bonded to this carbon, which is directly bonded to a pi system. This is known as allylic halogenoalkane. So there's a delta plus here, delta minus. So this is also considered primary. Yeah, it can undergo nucleophilic substitution via SN2, not a problem at all. Yeah, but SN1 is also not an issue, because if the CCl bond breaks, you'll notice that it's able to generate this particular carbocation, and it's actually quite stable. How do we know that it's quite stable? So if I'm going to draw up an orbital diagram for you to take a look, right? So we have the CC pi bond represented with the purple p orbital, and then we have the p orbital, which is empty, represented by the green loop. Okay, so you notice that the empty p orbital can form a continuous overlap with the CC pi bond. So this, you can also say that the positive charge is delocalized into the CC pi system, or you can say that because the three p orbital can form a continuous overlap, so the positive charge is delocalized across the CC double bond. Yeah, so this helps to stabilize the positive charge. Yeah, so for those of you taking H3, you can actually draw out the resonance structures over here. So how you can draw it is if you recall, resonance structures is represented by a double arrowhead. Yeah, so you can show the delocalization, okay, by starting from the pi bond here, and then you form another pi bond at the adjacent CC single bonds. Okay, and then of course the resonance structures will look like this with a positive charge at the carbon. Yeah, so the resonance hybrid will look something like this, with each of the carbon having a partial double bond character. So the positive charge is delocalized over the three carbon. Okay, so electronic effect and steric effect can help to provide exceptions to whether a particular substrate prefers to undergo SN2 or SN1. Okay, so for exercise 3.3, we have bromoethane reacts with sodium methoxide to form this particular ether. Okay, CH3, CH2O, CH3. You're supposed to name and describe the mechanism of this reaction. So clearly this is a primary substrate and it is unlikely to be stabilized by any means. So I would say that the name of the mechanism would be second order nucleophilic substitution, or bimolecular nucleophilic substitution. Okay, so in this case, what's going to happen is that I'm going to draw my sodium ethoxide to the left. Remember to draw in the lone pair of electrons. Okay, and then remember how we should be positioning the group. CBr will be horizontal. Remember to put your delta plus, delta minus. Okay, and then of course I'm going to put my H here, and then the group projecting inwards another H. The groups projecting out is a CH3, and then the lone pairs of electrons will approach the electron deficient carbon center and form a O carbon bond, and at the same time the CBr bond will break towards the Br. Okay, and then I'm going to draw in the transition states. So the transition state will have CH3O, and then partial bond formed between O and carbon. Okay, and then I'm going to draw the rest of the the groups in, and then this is a CH3, and then partial bond breaking between C and Br. Okay, Br here. Okay, and then this is the transition states with a negative charge. Okay, and then at the end of the day, remember, the cone turns inside out. So if you forget the cone energy, I'm going to draw the cone in like this. Okay, so I'm going to draw the cone turning inside out. So CH3O here, and then a carbon, and then a H, and then H projecting in, and then a methyl group projecting out, and then plus Br minus. Okay, many students forget about the leaving group, so remember this, you need to draw out the leaving groups. Okay, and this is like the cone turning inside out, so the cone originally is like that, so now the cone is being turned inside out. Okay, so this is known as inversion or stereochemistry. Despite not having a chiral center here, okay, let me repeat, despite not having a chiral center here, we still say that SN2 results in the inversion in stereochemistry because the nature of the mechanism is such that the transition states is being locked. It's like a triggered by pyramidal transition states. Okay, yep. So next, we are going to move on to discuss the strength of the CX bond and how it affects the reactivity between the different halogenoalkanes. Yep, so as we take a look at the 4 representative compounds, we have fluoromethane all the way to iodomethane. You realize that the C halogen bond energy actually decreases from 485 to 240. You can easily explain this by looking at the polarity between the carbon and the halogens. Yep. What determines polarity? So if you recall from chemical bonding, the electronegativity difference between C and F is the greatest, and the electronegativity difference between Ci is the smallest amongst the 4 halogens. Yeah, so because of that, it affects the CX bond energy, and at the same time, the stronger the bond, the shorter the bond. The weaker the bond, the longer the bond. Yeah, so what is more important here is that we need to understand that bond energy is affected by the strength of the C halogen bond, and that leads to whether you are forming a longer or a shorter bond. Yeah, one of the reasons why carbon and fluorine can form a much shorter bond as compared to carbon and chlorine, in addition to the electronegativity difference, is also because carbon and fluorine are in the same period. Yeah, so in terms of valence orbital overlap, to give the sigma bond, there is no orbital mismatched. For carbon and chlorine, carbon is in period 2, chlorine in period 3, so the valence orbitals overmatch. There's some degree of orbital mismatched. Yeah, so the carbon and chlorine cannot come as close as that between carbon and fluorine. Yeah, so naturally the bond length will be slightly longer, and of course at the same time the bond energy will be affected as well, because the electronegativity difference between carbon and chlorine is not as great as that between carbon and fluorine. Okay, so this actually affects how they react towards nucleophile. So as you have seen from the last line over here, CF bond is very strong, so fluoroalkanes extremely unreactive, and it's difficult to make them undergo nucleophilic substitution. Okay, from 3.1.2 onwards, you will encounter a series of nucleophilic substitution reaction that are very useful. Yeah, they will form the arsenal which you need in order to work on synthesis type of questions. And this particular section also show you the usefulness of halogenoalkanes or halogen derivative as a starting compound, because you are able to synthesize more useful compounds from them. Okay, so for a start, we have hydrolysis, or you can call it nucleophilic substitution with hydroxide to give you alcohols. Yeah, so alcohols is also a very important functional group. Yeah, so the reagents and conditions we need here is dilute sodium hydroxide heat. Okay, so this reaction is also known as alkaline hydrolysis. Yeah, so there is also something called acidic hydrolysis, which we'll cover later on. Yeah, so perhaps the most important is 3.1.3, where we are substituting the halogen for cyanides, okay, to form the nitrile functional group. Okay, why is nitrile important? So cyanide is actually a very dangerous reagent, because cyanide is isoelectronic with carbon monoxide. Yeah, so that means that if a human being ingests cyanide indirectly or directly, a small amount of it can kill a human being. Yeah, but why is it that despite being of such great danger, right, we are still using cyanide in our reaction? Yeah, because the formation of nitrile allows us to expand into other compounds. Yeah, so perhaps before we talk about the expansion, you might want to remember the condition, ethanolic KCN heats. So what is the meaning of ethanolic KCN? That means that you are dissolving KCN, which is an ionic compound, in ethanol. Okay, usually you heat it under reflux condition to ensure that the reaction goes to completion. Okay, the reason why nitriles are important intermediary products is because number one, I can perform both acidic and alkaline hydrolysis to give me carboxylic acid and its corresponding carboxylate salts. Yeah, so these are the two very important reactions which you should know, and it's not too difficult to remember their reagents and conditions. Simply heating them with dilute sulfuric acid heats for the acidic hydrolysis, or alkaline hydrolysis, heating it with dilute sodium hydroxide, and you heat it. Yep. I think the product should be quite obvious. Carboxylic acid, because you might want to know that a cyanide functional group, right, is actually a mask form of carboxylic acid derivative. Okay, so maybe I can emphasize it's a mask form of carboxylic acids derivatives, which it will be the second last topic in your H2 curriculum. Okay, so when we have a cyanide or nitrile functional group, the carbon takes on a partial positive charge, the nitrogen takes on a partial negative charge. Yeah, you do not need to know the acidic hydrolysis mechanism for H2, okay, but for H3 it will be important for you to try to work out its mechanism. Yeah, so generally I can give you a little bit of hints. So those of you taking H3, why is it that we need to do it under acidic condition? It's because the first step involves the protonation of the nitrogen group in nitrile, so it involves the protonation of this group. Yeah, so because of that, you created the conjugate acid, and protonating the nitrogen group makes the carbon more electron deficient than it should be, so it will then be susceptible to nucleophilic attack by water, and then in this case the pi bond will break, and then so and so on. Okay, so I'll leave it to you all to try to figure out how to draw the mechanism. But for H2, no need to know. Okay, but probably you might wish to know that the purpose of doing it in dilute acid condition is to protonate the nitrile nitrogen. Okay, another reason why nitriles are useful is because we can reduce it under this particular condition, and it's quite a special condition known as lithium aluminum hydride in dry ether, or you can also do it under hydrogen with nickel catalyst high pressure. Okay, so this particular synthesis, right, or reduction allows us to generate a primary amine. Okay, so you can see from here that because a nitrile has a CN triple bond, so in this case the hydrogen actually adds across the triple bond to give you the primary amine. Okay, yeah, so very useful reaction. So so far you have learned this particular important synthesis, so maybe I can just summarize it a little bit. So you can start off with again, I use the same example, say 1 chloropropane. Okay, so from 1 chloropropane, we can subject it to ethanolic KCN. So we have ethanolic KCN heat, and then in the process the Cr will be substituted with Cn, and I hope that from here, if you do a quick calculation, you realize that the number of carbon increases by 1. Okay, because the carbon in cyanide is also considered a carbon, obviously. Yeah, so that leads to an increase in number of carbon, so we usually call this kind of reaction a step-up reaction because it increases the number of carbon counts. And then from here, there are several things we can do. The most obvious one from the above, we can perform a reduction, so we can use lithium aluminum hydride in dry ether. Okay, so the reduction allows us to produce a primary amine, and a primary amine is a very useful starting material. For example, you can use it to make amides, okay, and or you can use it to continue to make ammonium salts. Okay, if not, you can perform a hydrolysis reaction, so we can simply have dilute H2SO4 heat, and then in the process we will be able to produce carboxylic acid. And do count the number of carbon you have drawn. Make sure that it corresponds to the number of carbon in your intermediary nitrile product. Okay, so next we'll move on to 3.1.4, where we'll be dealing with nucleophilic substitution of with ammonia to produce amine. Okay, so maybe I can just shift up a little bit. Okay, so let's say we want to start off with 1 chloropropane, right? So if I subject it to ammonia, excess ammonia maybe, okay, I will be able to produce this particular primary amine as well. If you do a quick numbering of the carbon, right, the one in purple has only 3 carbon, the one in blue has 4 carbon, due to the fact that before I reduce the nitrile, I already added a cyanide, which increases the carbon counts by 1. Okay, so this kind of questions tends to be asked in exams. So if you are asked to make a primary amine from 1 chloropropane with only 3 carbon, then you shouldn't be adding a nitrile or a cyanide. Yeah, if you're asked to make a primary amine with 1 additional carbon, then maybe the telltale sign is that I need to begin by subjecting 1 chloropropane with ethanolic KCN heats under reflux. Okay, yeah, so that brings us to the next portion on nucleophilic substitution with ammonia to form amines. Okay, so from here the condition is ethanolic concentrated ammonia heats in sealed tube. Okay, so there's a reason given to you here. Sealed tube prevent ammonia from escaping, and then ethanolic concentrated ammonia means concentrated solution of ammonia in ethanol. Okay, so remember this. Yeah, so first of all, if you look at the above, you will first produce a primary amine. Okay, maybe this is not very obvious. okay, I think that's fine. Yeah, I think you can tell that it's a primary amine because number one is the nitrogen is only bonded to one R group. Okay, so I'll just highlight one R group. Yeah. However, you will notice that compared to ammonia, right? The primary amine is a stronger nucleophile as compared to ammonia. Okay, because of the electron donating alkyl groups. Yeah, so that means that the primary amine will compete with the ammonia to perform nucleophilic substitution with another RX or halogen derivative. Yeah, so this competition will lead us to produce a secondary amine, and then subsequently a tertiary amine, and finally a quaternary ammonium salt. Okay, the mechanism is shown here. I will not go into details, but all I want to highlight is that I think number one, ammonia perform nucleophilic substitution. In this case, it's a SN2 reaction, so it's a rear attack, and in the process, you produce this particular intermediate, which has a positive charge on the nitrogen. So this is a full positive charge, and you notice that this is actually the conjugate acid of the primary amine which I am trying to form. And because of that, the bromide leaving group will probably undergo an acid-base neutralization with it to produce the HBr here. Yeah, some of you might be asking, wouldn't my ammonia react with the H as well? Yeah, that could happen, no problem. Yeah, so the ammonia can also react with this H to give you ammonium, and then in the end your byproduct is ammonium bromide. Okay, then in that case you might be asking, so is the mechanism drawn here correct? It is still correct, because the ammonia can either react with the conjugate acid or it can react directly with the HBr form to give you ammonium bromide. Yeah, so either way you draw the mechanism, that's fine. Okay, so I mean, that's fine on paper. In actual fact, of course, you probably want to do a little bit more studies lah. So if I have excess bromoethane, then it will continue to give me a secondary amine, and then so and so forth lah. Okay, so it will be I mean, it will be useful if you from here you try to continue from here to draw towards the quaternary ammonium salts. And I think this is required of you in exercise 3.4. So you are asked to continue the mechanism until you reach the quaternary ammonium salts. Okay, so I will just continue from here. I think it makes life a little bit easier. Okay, so what I'll do is I will draw out the primary amine. So I'm going to draw it out, CH3 carbon, a nitrogen, and then a H here, and then a CH3. Okay, so with a lone pairs of electrons, and then of course I'm going to perform a rear attack on the methyl bromides. Okay, and then remember to put the delta plus, delta minus. Okay, so this is a SN2. Okay, so a lone pair attacks the electron deficient carbon. The CBr bond breaks hydrolytically towards the bromine. And okay, and in the process, I'm able to generate the conjugate acids. So I'm going to draw out the conjugate acid. So CH3 carbon, and then CH3 here, and then carbon here, H, H, and H, and then this nitrogen will take on a positive charge because this is the conjugate acid of the tertiary amine. Yeah, so the bromide which leaves will then abstract a proton from the conjugate acid, and then now the NH bond will break towards the nitrogen to neutralize the charge. Yeah, so in this case I'm going to get the tertiary amine, okay, which looks like this with a lone pairs of electrons. The lone pairs of electrons comes from the hydrolytic bond breaking of the NH bond, and then plus HBr. Okay, so this is what we call a tertiary amine. Okay, the tertiary amine will continue to react, okay, because of the fact that it contains this lone pairs of electrons. Okay, so it will continue to react over here. So I'm going to draw this, and this with the lone pairs of electrons, and then I'm going to draw out the methyl bromide again, and then make sure you point them in the correct direction, and then make sure you write out the delta plus, delta minus. You notice that over here in the mechanism, I did not draw out the transition states, okay, or we did not draw out the transition state. So you'll be asking, isn't this double standard? Because earlier on, I did mention that you have to draw out, right? Okay, so this is not exactly double standard, because over here we are trying to showcase to you how we are going to produce the quaternary ammonium salts. So the details does not lie with the transition state. We're not asking you to draw one SN2 mechanism, but we are asking you to draw multiple SN2 mechanism. Yeah, so in this kind of situation, it is actually perfectly fine not to draw the transition states. Yeah, so I think you have to react according to the needs of the question. Okay, then from here a rear attack towards carbon, and then hydrolytic cleavage towards the bromo groups, and then what I'm going to get here is a nitrogen bonded to 4CH3. Okay, so this is known as a quaternary ammonium salt. Take note that the nitrogen no longer has any hydrogen, so it's no longer a conjugate acid of anything. Yeah, so I can't deprotonate it anymore. So that is why these whole salts will be precipitated out, yeah, in the system. Yeah, so at the end of the reaction, if the quaternary ammonium salt cannot be solvated by the system, it will be precipitated out. It really depends on the nature of the alkyl groups as well. Right, okay, so gonna move on to the next portion. We are done with 3.4. Okay, how do you know that you are going to get a quaternary ammonium salt at the end of the reaction? Well, if you are given a solid sample, you simply dissolve it in water, and then you add silver nitrates, and then you test the precipitate form with, say, ammonia, okay, which resembles what you learn in for qualitative analysis in the lab. Okay, yeah. Then I'm gonna move on to 3.2, which is on elimination. So truth to be told, I think I mentioned earlier on, elimination, for the purpose of H2, you are just required to know the conditions and the reagents required to produce the alkene from the halogenoalkanes. You don't need to know how to draw the mechanism. Okay, so basically the condition is KOH, or potassium hydroxide dissolved in ethanol, and then you heat it strongly. Yeah, and then in the process, you should be able to get the elimination products. Okay, you also notice that for elimination, one substrate becomes two. Yeah, so that also means that elimination is entropy driven. Yeah, so if we look at what we learned in thermodynamics, right, delta G is equals to delta H minus T delta S. Yeah, and because elimination is entropy driven, and it is likely that the delta H will be negative as well, due to the formation of a strong CC double bond. So delta H is also likely to be negative. So delta S will be positive. Yeah. If we are trying to decide whether elimination will be formed or substitution will be formed, right? Then if you are asked how can you control the product, let's say I prefer more elimination products, then from this particular relationship, you might be able to tell that I can play around with the temperature. So if I increase the temperature, I'm actually inflating the absolute value of T delta S, and that is likely to drive the reaction more towards the elimination side. But that is just a side remark. I mean, for your consideration and for your analysis during exams. Okay, and also, truth to be told, there are actually two different bases that are present in ethanolic KOH. One of which is OH minus, and another base is actually ethoxide. Okay, but I think it's not mentioned in the notes, so I think it's fine, doesn't really matter. But I think what you need to recognize is that if you prefer the substrates or the halogenoalkanes to undergo elimination, then you have to ensure that your potassium hydroxide is dissolved in ethanol. If you prefer it to undergo a substitution reaction, then you have to ensure that you do not dissolve your base in ethanol. Yeah, just make it aqueous. I think that will be sufficient. Of course, that is also subjected to the solubility of my substrate in water, in aqueous medium as well. So usually we don't just use aqueous medium. We use a combination of both. Yeah, so it depends on the percentage of ethanol and aqueous medium. I think in H3 you will encounter something called the solvent effects, but I will not discuss too much for this particular H2 set of notes. Okay, the mechanism for elimination, only second order elimination is being shown to you here. I will not go into details. If you wish to, you can read up more to find out. But what I can share with you is what I said to you at the start of the lecture. What I mentioned is that the elimination is better known as beta elimination. Okay, why is it better known as beta elimination? Yeah, because earlier on I mentioned that this particular carbon is known as the alpha carbon because it is directly bonded to the bromo functional group. Okay, and next to the alpha carbon we have the beta carbon. Okay, and this particular beta carbon contains 2 beta hydrogen which can potentially be eliminated from the system. And in the course of elimination, the Br is being expelled out and it leads to the formation of the CC double bond. Okay, so for elimination, it's better known as beta elimination for the one in your syllabus. And in order to predict the number of elimination products, you need to determine the number of types of beta hydrogen. Okay, so maybe I should write it here. To determine the number of different alkenes produced, you need to find out the number of unique beta hydrogen. Yeah, okay, so I'm sure there are examples later on which we can tap on. Okay, yeah, I think same story here. Ease of elimination depends on the strength of the C halogen bond because regardless of whether is it first order elimination or second order elimination, both involve the breaking of the C halogen bond as well. Okay, then yeah, sometimes more than one alkenes can be formed, and I think I mentioned here the reason is due to the number of unique beta hydrogens, okay, which we are going to illustrate using exercise 3.5. So over here, you are asked to draw the structural formulae of the 3-alkene formed when 2-bromobutane undergoes elimination with hot ethanolic sodium hydroxide. So first of all, we need to draw out the structure for 2-bromobutane. So I'm going to draw it out for you. So this is 2-bromobutane. Then next, determine the beta carbon. Okay, so this is the beta carbon. This is the beta carbon. Okay, so there are 2 different types of beta carbon. So that also means that I have 2 different types of beta hydrogen. So I call this HA and I call this HB. Okay, so that also means that in the course of elimination, okay, so hot ethanolic NaOH. Yeah, so in the course of elimination, I'm going to form an alkene first by eliminating HA and Br. So this is what I'm going to get. Okay, and then next by eliminating HB and Br. Okay, but you notice that when I eliminate HB and Br, I will end up with a pair of cis trans isomers. Okay, so I can get this like this. Okay, so altogether there are three different types of alkenes, which allows it to undergo elimination under the appropriate condition. And then I'm sure you might have remembered from the alkene chapter that in order to determine which is the more prominent alkene or the major products being formed, right, you have to find out the number of alkyl groups bonded to the carbon in the CC double bond. Okay, so in this case we have one alkyl group bonded to the carbon. Okay, in our other two cases we have two. Okay, so that means that this is what we call a mono substituted alkene. Okay, and these two are di substituted alkenes. Yeah, so in terms of stability, the greater the substituent pattern, the more stable is the alkene. So a di-substituted alkene is more stable than a mono-substituted alkene. Yeah, so I expect these two to be formed in greater proportion. Okay, then of course there's for your information here, so this is known as Zaitsev rule. Okay, so I think I mentioned that the greater the more alkyl groups, the more stable is the alkene isomer. Okay, then next we have exercise 3.6, where we are supposed to fill in the boxes with the correct reagents and structures of compounds in the reaction scheme. Okay, so first of all, we have ethanolic sodium hydroxide heat. Okay, so let me just highlight the beta hydrogen. So this is alpha, so beta hydrogen is here. Yeah, there's only one unique beta hydrogen, so I'm only going to get one unique product, which is propene. Okay, the question asks for structures, so I do not need to draw displayed formula. I just need to draw out skeletal structure. Okay, then next, you notice that the Br is now added to the middle. So this is what we commonly call electrophilic addition of HBr, because in the process a secondary carbocation is being formed, and then after that the bromide will undergo a nucleophilic attack towards the secondary carbocation to give you this secondary bromoalkane. And then with ethanolic KCN, you know that ethanolic KCN replaces the bromo group. Yeah, so in this case I'm going to get a CN here. Okay, CN here. Some students ask me, can I draw CN like this? Okay, this is not a problem if it doesn't confuse you. If it confuses you, then I think it's better to just draw CN as CN. Because if you draw it like this, imagine that two pi bonds at the side, if you draw it a little bit longer and it touches the carbon here, then something is very wrong. So I think it's better to just write out the CN. Okay, and then for step 4, you notice that the C triple bond N is being reduced. So of course what we're going to have here is lithium aluminium hydride in dry ether. Okay, so remember, no warming is required. Okay, next we will move on to the reactions of halogenoarenes. Okay, so the key learning objective here is that the chlorobenzene is relatively unreactive as compared to the other halogenoalkanes. So what is the reason? So over here we give two very simple reasons, but they are sufficient for you to go through it and then understand. The first reason is due to the partial double bond character. Yeah, so remember that all the halogens, whether is it fluorine, chlorine, bromine, or iodine, they contain lone pairs of electrons, and the lone pairs of electrons, one of them lies in the p orbital. Yeah, so this lone pair will be delocalized into the phenyl ring. So that means that the lone pairs of electrons will overlap continuously with the pi electron clouds in the benzene ring. So when this happens, it gives the C halogen bond a partial double bond character. So this leads to the strengthening of the C halogen bond, making it more difficult to break or making it less susceptible to nucleophilic attack. Okay, and in addition, right, you notice that nucleophilic substitution, if let's say it's going to undergo a SN2-like mechanism, right, so you will be expecting the nucleophile to approach from the rear of the C halogen bond. So in this case, the rear of the C halogen bond is over here. Okay, it's over here. Now, it's very difficult to approach from the rear like this because you notice that your benzene ring blocks the approach by the nucleophile. Yeah, so because of that, the rear of the C halogen bond is directly very bulky, so it will repel incoming nucleophile. Okay, so it will tend to repel incoming nucleophiles. Okay, so remember this. Yeah, so these are the two most important reasons why halogenoarenes do not tend to undergo nucleophilic substitution. Okay, unless I mean, it's not impossible, it is possible, but you need to heat it under very harsh condition, and of course at the same time you can modify the substrate, which you will probably encounter in other mediums lah. I mean, I won't go into details now. Okay, what about electrophilic substitution of benzenes, of benzene ring of halogenoarenes? It will happen, not a problem at all, but do take note that the halogen tends to be electron withdrawing via the sigma bonding framework, because the halogen bonded to the benzene ring is more electronegative than the carbon next to it. Yeah, some of you might argue that, hey, but the lone pairs of electrons delocalize into the benzene ring, what? Then shouldn't it increases the electron density of the benzene ring? Well, it does increase a little bit, I guess, but not so significant, largely because of the orbital mismatch between the halogens and the benzene ring. Yeah, and I mean the pi electron cloud in the benzene ring, because if you look at chlorine, bromine, and iodine, right, they tend to use, or the lone pairs of electrons tends to reside at the 3p, 4p, and 5p orbitals, which are much bigger in size as compared to the 2p orbital in the carbon in the benzene ring. So that makes it difficult for the electrons to delocalize all the way into the benzene ring, but perhaps just form a partial overlap with the carbon directly bonded to it. Yeah, so because of this, the sigma withdrawing effect tends to dominate a little bit more, and that makes halogenoarenes less susceptible to electrophilic substitution. And because of that, I need a harsher condition to effect electrophilic substitution types of reaction. So in this case, the example we gave is nitration. Okay, yeah. Then if you're going to take a look at exercise 4.1, we are supposed to state whether the following reaction take place in the respective halogen containing compounds. Okay, so first of all, we need to establish some facts. Okay, so this is a primary chloroalkane. This is a chlorobenzene. Okay, and in our case here is a primary chloroalkane. Yeah, so do take note of this. The carbon, or rather the chlorine, is directly bonded to a sp3 hybridized carbon. Yeah, So chloromethylbenzene is still considered a primary chloroalkene and not a chlorobenzene. Remember this. Okay, for delocalization, a little bit of the electron density on the p orbital of on the 3p orbital of chlorine will delocalize into the benzene ring, but just a little bit of it. Actually, the fact is that it forms more of a partial double bond character with the carbon directly bonded to it rather than it delocalizes all the way. Yeah, but the sigma withdrawing effect dominates. Okay, nucleophilic substitution, of course, it occurs, and this occurs as well. Okay, but for the case of chlorobenzene, then no. Okay, not possible. What about elimination? Okay, so let me just highlights the beta hydrogen. So for chloroethane, these are the beta hydrogens. Okay, for chlorobenzene, there is no beta hydrogen. Okay, so oops, shouldn't be this. Okay, so the beta hydrogen is actually here and here. Okay, so potentially chlorobenzene could undergo elimination. However, you will learn maybe at higher level that it's not possible to abstract the hydrogen in the way you want it to abstract. And also, if it's going to abstract the hydrogen this way, right, the pi electron cloud will be orthogonal to the pi electron cloud of the benzene ring, and this makes the compound highly unstable. Yeah, so I would say elimination for chlorobenzene, although it contains beta hydrogen, is unlikely. Chlorethane possible, and chloromethylbenzene not possible because of the lack of beta hydrogen. So lack of beta hydrogen. Okay, so not possible. Yeah. What about electrophilic substitution? Of course, chlorethane no, but for the other two, yes. Yeah, doesn't really matter here. Okay, so chlorobenzene will probably react a little bit slower as compared to chloromethylbenzene. Okay, but they can still undergo electrophilic substitution due to the presence of the phenyl ring. Alright, then we'll move on to the next section, which is on distinguishing tests. This particular section is very useful for laboratory work. Yeah, so I will probably spend a little bit of time on it so that you know what exactly is going on. Okay, so first of all, right, we need to compare the color of the silver halide precipitate. So a general method of distinguishing between the different types of halogen present, right, is to look at the color of the precipitate, which precipitates out from the solution when you add silver nitrate. Yeah. So first of all, right, we need to recognize that the halogen is sigma bonded to the sp3 hybridized carbon in the halogen derivative. Yeah, that is very important. So before precipitation can take place, what we need to do is to allow nucleophilic substitution to take place first. Yeah, because in this case, we will be able to get the free halides. The free halide is important because once the free halide is out, when we add silver nitrate, then ionic product of the relevant silver halide will exceed its KSP, and because of that, precipitation will occur until IP equals KSP. And if you don't know what I'm talking about, please go and review your solubility product notes and maybe the video lectures as well. Yeah. So after performing nucleophilic substitution, which is the first step, the second step, I need to add dilute nitric acid in order to neutralize all the OH minus. Yeah, because if I don't do that, I might introduce the formation of silver hydroxide, which eventually will give me this silver 1 oxide, which is undesirable because the solution will be very messy. Okay, so it's important for us to add dilute nitric acid. I hope you also understand why we can't add hydrochloric acid, because if we add hydrochloric acid, we are introducing chloride, which defeats the purpose, right? We try not to add sulfuric acid because although silver sulfate is quite soluble, Okay, I mean not so soluble but not so insoluble. Yeah, but sulfate sometimes can complicate matters. So we try not to deal with it. Yeah. Okay, then step 3, we're going to add silver nitrates and then observe the color of the PPT. Okay, but sometimes the color can be difficult to differentiate, especially silver chloride and silver bromide. Yeah. Silver iodide is also a little bit difficult because the yellow is very pale. Yeah, sometimes it looks a bit more like cream, and then cream seems to appear a little bit more like white. Yeah, so the confirmation test we can do, right, is to test for the solubility of the silver halide by dissolving it in aqueous ammonia. Okay, so in our case here, you need to, if you recall from practical 15 or 15, okay, you need to decant away the solution in order to test for the whether the silver halide will dissolve in ammonia. Yeah, so in our case here, it's also in your QA notes. Silver chloride can be easily dissolved in dilute aqueous ammonia. Silver bromide only in concentrated ammonia. Silver bromide can partially dissolve in aqueous ammonia as well. And then silver iodide insoluble in both. Solubility is due to the formation of this particular colorless complex known as diamine silver 1 complex. Okay, if you need more explanation, please refer to solubility equilibrium notes. Okay, yeah, I have explained quite extensively over there. Yeah, so you might want to refer to that. Sometimes we are required to compare the rates of formation of silver halide precipitate. Yeah, so in our case here, what we're gonna do is we will place 1 cubic centimeters of organic compounds in a test tube. All these are in 3 separate test tubes. Okay, and then we will add 1 cubic centimeters of ethanolic silver nitrate inside. Again, ethanolic silver nitrate means silver nitrate dissolved in ethanol. Okay, because in the presence of ethanol, right, it will enhance a little bit the breaking of the C halogen bond. Okay, so if you want to find out a little bit more why is that the case, yeah, please go and read up on other resources. Okay, so we'll deal with it when the time comes. And then now remember this, in our case here, right, we put all the 3 test tubes in the same hot water bath. Okay, and then our job is to check which of them amongst the 3, right, which one forms precipitate first. Okay, so in the case of iodoalkane, the yellow PPT form almost instantaneously. Yeah, so that means that immediately when I added ethanolic silver nitrate, right, quite a lot of the Ci bond is already broken, which results in the presence of iodides. And then because I have a lot of free iodide in the medium, so the ionic product of silver iodide will exceed its KSP, which leads to the formation of silver iodides. Okay, and then for bromoalkane, the cream PPT will form at a longer time. Okay, so maybe one is instantaneous, the other one is maybe after 1 or 2 minutes, and then for chloroalkane, it forms probably in about 8 to 10 minutes time. Yeah, so for 5.2, right, and 5.1, they are a little bit different, so I hope you don't get confused. 5.2 is to compare the rates of formation of the silver halide precipitate. Yeah, so we subject all of them to the same condition. We do not need to observe the color of the precipitate that clearly, although of course it's important. Yeah, but we are just trying to see amongst the 3 which one produces the precipitate first. Of course, Ci bond is the weakest, more likely to be broken, so produce the precipitate first. Okay, and then blah blah blah. For 5.1, what we are interested in is not the rates, you notice, because in step 1 I have already hit the respective halogenoalkanes with sodium hydroxide. So after step 1, right, nucleophilic substitution already completes. Yeah, so after I perform step 1, all the 3 different test tubes have the same amount of free halide. So the same amount of free halide, right? If you dump in silver nitrate, of course the precipitation for all will occur at the same time because they already have the maximum amounts of free halide. So this is a little bit different from 5.2. Okay, so if you are confused about difference, you may want to read them again and then get familiar with the concepts. Okay, then I've explained to you why is there a difference in the rate of formation of the silver halide precipitates. It has got to do with the breaking of the C halogen bond. The stronger the C halogen bond is, the longer it takes to break. Okay, so Ci bond is the weakest. Yeah, so that's why you observe the formation of yellow precipitate or silver iodide the fastest, almost instantaneous. Okay, next we'll look at exercise 5.1. So we have a liquid L, gave a pale yellow PPT when shaken for some time with coethanolic silver nitrate. What could L be? Okay, so first of all, I need to look out for an iodo group directly bonded to sp3 hybridized carbon. Okay, so I think this is obvious. Okay, so I'll pick 1, and I think this is obvious as well. I'll pick 2. Okay, in our case here, the iodo group is directly bonded to the sp2 hybridized carbon in the benzene ring. So due to the partial double bond character, under this not so harsh condition, I don't think the iodo group will become free. So in this case, I'll choose options 1 and 2. Okay, then moving on to exercise 5.2. Which sequence shows the correct order of decreasing ease of hydrolysis? Okay, so again, we need to look at the key term, decreasing ease of hydrolysis. So that means that the one which is able to undergo hydrolysis the fastest should be right in front, and preferably that contains a Ci bond. Yeah, if not a CBr. Okay, so in this case, the CBr is in the middle. I won't pick option A. In this case, the Ci is in the middle. I won't pick option B. In this case, I have a halogenoarenes here. One is a bromo, one is a chloro. I don't think that will work, so C is wrong as well. And then this is a CBr, which is weaker than a CCl. And then at the same time, the Cl bonded to the sp2 hybridized carbon, which is part of the benzene ring, has partial double bond character. Yeah, so because of that, I think this is the correct order. I'm going to pick D. Okay, so the MCQ, I hope you don't find them too daunting. Generally, they are testing you on some of the basic concepts which you have learned earlier on. Okay, then for section 6, I think I can leave you to read on your own. It's basically referring to the uses of halogenoalkanes and the environment. Yeah, so number 1 is the making of Teflon, which is a non-stick coating on the pots and pans. You might have read that the Teflon is actually not very good for health, because if you heat it above a certain temperature, you do expect some of the fluoro group to escape, and then it goes into your food. So I don't think that is very nice, and that's why Teflon is not a very Teflon coated coatware is not very popular nowadays. Okay, and then for CFCs, it has been used in the past, as refrigerant, coolants, etc. Nowadays less, maybe more in fire extinguisher. Okay, so they have some useful properties. Inert, non-flammable. I think we talked about it earlier on. C halogen bond very strong. Non-toxic, and then they can be easily liquefy, because they form strong instantaneous dipole-induced dipole interaction or strong dispersion forces with one another, so they tend to have relatively high boiling point, and then they do not stink. Okay, and then of course here you can read about the ozone depletion. how does CFC results in ozone depletion. The one which results in ozone depletion is more of the C-chloro bond rather than the CF bond. Okay, so you can read about it here, largely due to the presence of the UV light, which allows homolytic cleavage between C and Cl, okay, rather than C and F, because CF bond is too strong. Okay, then because of that, it leads to the depletion of the ozone layer, because the oxygen atoms being formed, right, will continue to react with the chloro radical. Okay, so over here, because the chloro radical react with ozone, give us a ClO radical, and then the ClO radical will react with the oxygen which is produced from the natural process due to the homolytic cleavage by absorbing UV light from the sun. Okay, and then from here it leads to the production of another chloro radical, which will continue to react away the ozone layer. Okay, so that is something which I mean, if you are very passionate about environment issue, I think you should maybe read a little bit more about them. Okay, then what are the measures to protect the ozone layer? So of course, reduce use of CFCs, and then use some substituent. For example, propane or butane, but usually they are quite flammable. So I think we are still in most cases we still use CFCs, but we try to limit its use because of the harm it caused to the environment. Yeah, so maybe something interesting for you to think about is, are you able to maybe you can try to read out a little bit more what are the other alternatives to CFCs in addition to using pure alkanes. Okay, finally we have exercise 6.1. You were told that CFCs have been widely used in aerosols, sprays, refrigerators, and in making foamed plastics. Okay, so now known to destroy the ozone layer. Okay, so which of following will not destroy ozone layer? Okay, and can be used as a supplement. Okay, definitely we are not going to choose this because it contains CBr bond, which is even weaker than CCl. Okay, we're not going to choose this because it contains CBr bond. Okay, we're not going to choose this because it contains CCl bond. Okay, so the best example we can choose is butane, because it doesn't contain any CCl, CBr, or Ci bond. Okay, which makes it safe. Yeah, if it's pure CF4, say, let's say CF4, I think that should be fine as well. Yeah, but in this case we don't have any of them, so I'm just going to choose a pure alkane. Okay, so finally we are here. There are some we give you some summary of the key reactions which you need to know for halogen derivatives. So please go and find out what are the reagents you need from 1, 2, 3, 4, 5, 6, and 7, 8. Okay, and of course for halogenoarenes as well lah. Yeah, so after you have done them, please check your answers online. Okay, so that will be the end of my lecture on halogen derivatives. So the next one that's coming up will be on alcohols, and I'll see you then.